Yes. No.
Good morning, all. Is it audible?
Yes, sir.
Okay.
Yes, it's audible now.
Yes, sir. Thank you. Thank you. Good morning, all. Welcome to third day FDP program on applications of artificial intelligence in brain-computer interfacing. Today, we have session with Dr. Rakesh Gupta. He is my colleague, friend, well-wisher. He is a cognitive scientist. He is from SR University. Today we have a session with him. Now I'm going to introduce about him in short duration. Dr. Rakesh Gupta, working as Assistant Professor and Director, Center for Cognitive Creation, SR University, Warangal. He is a cognitive scientist, vision, attention, and working memory. While working on his dissertation, Rakesh spent 2 years as a visiting fellow at Center for Mind-Brain Science at the University of Trento, Italy. He completed his PhD from Center for Neural and Cognitive Science, University of Hyderabad in 2015, with a thesis entitled Computational and Empirical Investigation on Number, Time, and Memory. Upon completing his doctorate, Rakesh spent 2 years as a postdoc at Center for Vision Research at York University in Toronto, Canada. His current research involves building a visual working memory module for selective tuning based cognitive architecture, as well as building computational models of the human motor system using computational theoretical, behavioral, and neuroimaging methods. He is also reviewer for Journal of Cognition, and he had a lot very good publications in reputed journals, as well as he had good patents. He's a good researcher now, and is a good scientist. He's my colleague. Now I'm going to I am requesting Dr. Rakesh Gupta to start the session. Thank you, one and all.
Thank you, Ravichandra, for the kind introduction. I hope I am audible to everyone. So today we have a tripartite, if you will, a topic for the purpose of this FDP. I want to share, we can't uh, get through the entire topic in just one lecture or even this entire FDP, but I'll try to do my best. So I hope everyone can see the PPT that I am sharing. If it is visible, please let me know. Is it visible?
Yes, sir, it is visible.
Okay. So, for the first part, there are two parts to this lecture. In the first part, I talk about mainly AI and cognition, and then in the second part, we go on to the BCI aspect. And those of you who have attended the first day's session conducted by Dr. Ashok Rao, some of the beginning parts you might find very familiar. He had wealth of information to offer for all of us. Now, when we talk about AI in public perception, there are a lot of movies and other things have been made, but in reality, it's a lot more intricate and it's already part of our lives, even if we don't know it. If you just open any tech journal or even mainstream media articles, you would find some topic that touches the boundary of AI and human society. Now, this has been possible over the last 10 years because of the rise of big data and deep learning methods in AI. But and also there are so many different kinds of futures that are being imagined. For instance, this is the front page of IBM's site, IBM Watson, where they offer that you can take a personalized AI assistant just for yourself. And that's amazing. It AI tailor made for you. It doesn't do very complicated things, but it can make our lives easier. And so we keep on our researches. If we keep on producing different kinds of miracles, some of the more far-fetched science fiction concepts may not be out of our reach in the near future. Now, if this has been spoken by Dr. Ashok Rao and others, that artificial intelligence research actually dates back to 1950s. In fact, the artificial intelligence and cognitive science began in neighboring labs, if you will, in Stanford and other big Ivy League universities. But it took quite a lot of time for it to come to so mainstream and out of science fiction because of certain changes that have happened in recent years. One of the most important things that have changed the landscape of both artificial intelligence and technology landscape is big data, because we have so much of humongous amounts of large databases available. We have easier collection and storage, and hardwares have improved exponentially. We have now graphics processing units which can do multi-threading operations that were not thought of until that's 10 years back. The massively parallelizability of these GPUs offer something beyond what other CPUs, even hardcore CPUs that we used to use just 10 years back. And of course, softwares have improved considerably. Newer models, newer toolboxes. In fact, those of you who are interested in just starting out with any deep learning or other kinds of neural networks, you can check out Google's TensorFlow. It's freely available. You can tweak it. Even you can make simpler models by just yourself. Now, in fact, again, this part also should be familiar to you from the previous lectures on AI, that when we talk about the big picture, we have AI, we have machine learning, and part of the machine learning can be done through neural networks and expert systems. Now, I'm going to specifically focus on, for this lecture, this subset of machine learning that deals with neural networks, and we'll see why. Now, artificial intelligence and cognitive science are both engaged in understanding intelligence, but the perspectives are slightly different. AI has the commitment to design intelligent systems or artifacts that mimic humans and other intelligent beings. Whereas in cognitive science, the commitment is to understand intelligence, primarily human intelligence, by employing formal, computational, and empirical methods. Now, to that end, there are four different kinds of approaches to AI are given in one of the best textbooks for artificial intelligence available in the market right now, Russell and Nordvig's textbook, named appropriately Artificial Intelligence. And there they talk about, when we talk about AI, we can think of these four quadrangles based on thinking versus acting. So thinking humanly versus thinking rationally, acting humanly versus acting rationally. So there are four different axes, whether you're thinking or whether you're acting. and two different ways of making that happen. Are you going to go about it rationally, or are you going to go about humanly? Now, it might be a bit odd to see that thinking humanly or acting humanly being in contrast with thinking rationally or acting rationally. To that end, this is where the very interesting conundrum of most of AI research lies, that what we think as the most rational solution and even defining rationality becomes a humongous challenge when we come to AI, because we need every definition looked at much more carefully. To think of it, when we talk about humanly versus rationally, if I now ask you very simply, what is your favorite color? And all of you will have something to say about it. How are we able to do that? How are we able to prioritize, give relevance to something like to the wavelengths of light? And they should all be same to us. It doesn't matter. Because if we put it in pigments, they don't interact with us, but yet we have a preference. And this idea of how we can form these preferences, give relevance to things, that is uniquely human aspect, which cannot be matched by the latest cutting edge AIs even now. Whereas thinking rationally has to do with how do you process odds, how do you process probabilities, which humanity is not very good at. Those of you who are interested, you may want to check out something called the multi-hall problem, which I'm not going to go into, that how human beings can make mistakes in judging probability. But given the above, I now want to throw that why we talk about this. I'll give you with an example. For instance, you have reflex action, such as flinching from a hot stove. If you touch something hot, you flinch. Is it a rational? Are these reflex actions rational? Are they intelligent? And then there is a higher order question. How could introspection or reporting on one's inner thoughts be inaccurate? Could I be wrong about what I am thinking? If you now take these two questions, you can slowly start to parse out the challenge that lies in front of us. In fact, one of the ways of human thinking, human language, is what we call recursive, because we can think about our own thoughts. We can have a thought about our thoughts that are going astray. So much of our language is based on that. So much of the way we think, we constantly are thinking in first, second, third order. When you do an action, you are not just thinking about how this action is going to affect the environment. You are looking at the actions past, actions future, how other people will interact with it. And that complex decision chains are yet to be mapped in its entirety in most AI systems. Now, why there are so many AI problems? If you think about, that most real world problems suffer from what we call the combinatorial explosion, which can be seen in even the first AI that was built, and ultimately, the human beings were defeated in front of the AI because of the starting positions that lead to multiple different combinations, which again diverge further. And this is just a well-defined, rules are defined in games of chess. But when you come to the real world, most problems do not have all the information. You lack information, you lack all the rules, you lack ideas about clear causal relations between past and the future of events. And that makes all the AI problems much more problematic. Now, this part I'm going to skip, but the idea of the modern AI, modern artificial intelligence with deep learning, came around 2012 with AlexNet, which won the biggest competition of image processing. That's the ImageNet, and it left all the other traditional statistical and other methods of classification far behind because of a convolutional neural network architecture. And modern AI has come so far, but the roots of it lie in one of the first artificial neurons that was built, that is the perceptron, way back towards the left. In this lecture, I'm going to, in the first part, I'm going to draw a line from this perceptron to the bigger deep learning networks and how can we come in with the help of different kinds of ideas about biological cognition. So now, now consider this, like how does an AI learn? This has been spoken about in a bit more detail and in depth by Dr. Ashok Rao before, but if we summarize, major points are AI learns by two-way conversation with the user. It learns by being told what is true. It learns by being shown examples of what they are required to interpret. And it learns by actively investigating their environment and learning from what they find there using trial and error or intelligent observation. And they also learn by logical reasoning from what they already know. By the way, there is not a single machine which can do all of it together. We have these different kinds of AI, different kinds of learnings, and which is why in the more AI community, more talks are coming in about the systems of experts. Whereas some experts can do two-way conversation, some expert systems can do logical reasoning. Can we have this system of experts and like work coherently so that they come to resemble human intelligence as we know it in a better manner or even surpass it? And that's the idea, right? Like, we human beings, our abilities are generally smaller. If I ask you now to lift a 100 kg stone, you can't do it. That's why we invent machines, because we can't humanly lift a 100 kg rock just by ourselves. And that's where the essence of it is. It's not that we want the AI to think and act in a human manner, but probably to do something better than what we were able to do. And that's where we want to go in the future. But the order in which the AI program executes instructions are always can be unpredictable. Solution to the problem proposed by AI method may not be unique. Instead, several answers may be offered, each with certain level of confidence. While AI may not be completely sure of the answer, its ability to deal with uncertainty endows it with considerable flexibility, so that most AI methods can be applied to problems in which data themselves are uncertain. And that's why we are pushing AI more and more out there in the world, because to handle some of these uncertain problems and not having a human being look over all the time for everything. Now we are coming to neural network. Neural network, or we can talk about artificial neural network. I talk about artificial neural network as opposed to biological neural network, which is similar, but biological neural network has more commitment to biological fidelity and biological plausibility, whereas artificial neural networks do not. Most of the deep learning networks are basically fall under the artificial neural networks frame. So this is artificial neural network systems are information processing systems loosely based on the model of biological neural networks. They're implemented in softwares or electronic circuits, and defining properties are they consist of simple building blocks, neurons, which must be able to learn, they must be able to generalize. And the biological inspiration comes from that human brain has about 10 to the power 11 neurons. Now, human neurons have dendrites, which have incoming information, incoming extension, they carry the signal in, actions carry the signals out, and the synapse forms a connection between two neurons, and which learn by changing the nature of those connections. New connections form, which means that you have learned something new. Even when connections separate, which means that your brain is learning something else, trying to cut out redundant what do you say connections. Now, there are different types of neural networks are available. They can be classified based on different kind of attributes like applications or connection type, topology or learning methods. And some of it again has been spoken for in the first day, so I'm not going to go deeper into it. And there are different kinds of applications of neural networks. Now here, they have applications in aerospace, banking, defense, financial, manufacturing, as well as biomedical and medical image analysis, including brain-computer interfaces, robotics, pattern recognition, in anything that you can think of. Now, to go to the first level, we are going to show you the difference and similarity between biological and artificial neuron. As you see that we can model the biological neuron into the simplest perceptron. This was one of the first artificial neural network modules developed. So this perceptron gets inputs from outside and weighted inputs. This W's mean weights, and then they are summed up and they are passed through something called a non-linearity. So it's not the simplest sum does not become an output. Simplest non-linearity you can have by having a threshold that if the like weighted sum is less than a certain value, then the neuron will have an output of 1, otherwise 0. That in itself is non-linearity. It's non-linear because that you can't have a linear function mapping between the 0 and 1. Now, these weights model the synapse between two biological neurons. Now, each neuron has a threshold that must be met to activate the neuron, causing it to fire. And the threshold is modeled after the transfer function, sigma or g, as we are going to call it. And they can be excitatory, causing other neurons to fire, or inhibitory, preventing other neurons from firing. Now, this is our simplified perceptron. I'm not going to go in deeper into the mathematics of it, but we are going to talk about how training of these kind of systems work. Any artificial neural network, including perceptron, starts from a position of complete ignorance. So a training period is required where it can be let loose on real life problems. And during training, the novice perceptron is shown examples of what it must learn to interpret. And these examples constitute the training set, and these constitute two parts. Training stimulus is a collection of inputs to the perceptron. Associated with each stimulus is a training target, which is a desired output or the right answer for each stimulus. If the output of the perceptron is correct, do nothing. If the output of the perceptron is on but should be off, then decrease the weights. And if the output of the perceptron is off but should be on, increase the weights. And these were the first simplest rules for perceptron training, and they are known as Hebbian rules by the name of one of the better psychologists of first half of 20th century, Donald Hebb, by his name. So this Hebbian learning rule, when it was proposed, the perceptron could do some things very well, but it did not do everything, because with a single layer perceptron, it could only solve problems that were linear. Any problem that involved nonlinearity, it could not solve. For instance, it could solve the problem of simple dogs versus cats, and you can see that if you put these pictures are basically when more and more examples are being added to the training set. First, one dog and one cat are given, so the system tries to classify them according to the line. But then you have the two factors or the two features according to which the classification is being done: size versus domestication. In the second image, another dog is added, so the line skews somewhat, because otherwise it would be wrong if it kept the original line. Similarly, more cats are added, more dogs are added, so the line keeps adjusting. So this is a very simple classification that a perceptron can do by changing its weights and the outputs. Now, the purpose of the activation function is to introduce non-linearities into the into the network. Now, let's say we want a network which can distinguish between these reds and the green points. If we have a simplest single linear activation function, then we can't make that decision. But we can make it if we have a non-linear activation function, and which is why activation functions or the sigma or G, as we are going to call it, become important. These are some of the functions that are used in general in the most of the neural networks and machine learning literature. Sigmoid, hyperbolic tangent, rectified linear unit. Mind you, ReLU units are some of the biggest components of the deep learning and convolutional neural networks. These need to be paid special attention. You can take this. You can find those in MATLAB also. There are there are hard limiter, symmetric hard limiter, linear, log sigmoid. There are some of the other competitive, some of the other functions that are available for you to build your own different kinds of neural networks. Now, the problem with all of this, that when we try to build this, solve this problem of separating or learning a pattern, one of the things that we should be aware of that we can end up overfitting our data. When you throw massive amounts of data and try to training data and try to train it for all possible patterns, it might be possible that you are overfitting your data, and that's something to always watch out for. If you see that, on the left, there is a very bad fit. In the middle, there is a fit that can be acceptable. But if you see the third picture, which fits the data much better than the middle image, but you know that the actual function should not be like that. And this is where both principles of Occam's razor and and some common sense must prevail. So, why do we not go for this overfitted graphs? This overfitted graph did very well for the training set. But if you now consider the factor where more and more data will pour in, then it will become more and more wrong because it is very tailor-made to fit just the training data. Whereas the middle one will do considerably well even if more points and more data points come in. Now, we talked about this now from artificial neuron. Can we really go to a network? So let's come back to our simplified perceptron. So which has inputs, weights, weighted sum, non-linearity, which goes into an output. Now this can be represented very simply as this matrix format, like you have the output, which is basically from the weighted sum, and then added the non-linearity function. Now you can think that why do we have to limit to just one output? Can't we do two outputs? Of course we can. And again, those multi-output perceptrons are well built. Now, what if we want those to be the more layers to be added? And this was first three-layer networks where the first connectionist models, which became very famous for solving all the problems that single-layer perceptrons could not. But as you can see, the nature of these functions look like almost like matrix multiplications. So it's basically each layer you multiply until you get to the output. And this taken far enough, you get basically a deep neural network. Because here, instead of thinking of all of this as simple weighted sums, you can think about doing an entire operation like a filter onto all the neurons. All the convolutions can be added up layer by layer until you get the deep neural network. In fact, some of the first deep neural networks are built like this. Of course, now we have different networks, units, all of those are very different. You can play with the nature of the neuron, nature of the activation function, like how many numbers of neurons you're going to put, what will be the ultimate classification technique, are you going to do softmax, hardmax, whatever you want. Now, but the problem with all of these multiple layers is that generally the outputs for this intervening layers like the Z layers that we see here are not available to us at every step. We generally, what we have available is the output and in the end. And then if the output is in error, then we need to find a way to send the error back and correct all the weights. But the operations are only on the weights. So we actually don't know what the outputs were in those inner hidden layers. And that's the nature of it. That's the nature in which these deep neural networks are built. Now, if you see, this is the more modern architecture. This is like a VGA 14. It's slightly outdated, but you'll see that it starts from it's an image classification for computer vision. So it starts off with a digitized image, which goes through these simple filters. Each filter corresponds to one neuron. And this neuron acts as if it's going to apply a filter to the image. And those filters also can be of multiple kinds. But as you see, initially the filter sizes are very small. This is 5 by 5. Next layer 27 by 27. Then you have like, size of, then again you can reduce the size, like, or increase the size. You can go 13 by 13. Then again to 2048, like, and again a big dense layer you can put over there. So how you are going to put all of these architectures, what will be the number of neurons, what kind of sizes of what will be the size of the receptive fields of these particular neurons, what kind of filter you are going to apply, all of these are on your own, and you can play around with it as much as you can. And it offers a very like, high reward from all the outputs that you can get. And which is why deep learning is the way to go if we want to go be technologically sound. But of course there are failures. Like, this is from Russell and Norwig's artificial intelligence. The summary of the quote actually means that we have not considered that what if we actually succeed in making an AI completely fully functioning AI. That is something that we don't often think about. And why that needs to be a caution, we need to talk about some of the other researches that have happened recently. So one of the University of Maryland researchers created 1213 questions in collaboration with computers to identify flaws in machine learning language models. So for instance, if the author writes, what composer's variation on a theme by Haydn was inspired by Carl Ferdinand Pohl, and the system correctly answers Brahms, but the interface highlighting the words Ferdinand Pohl to show that this phrase led to the answer. Now, using that information, the author can edit the question to make it more difficult for the computer without altering the question's meaning. For example, the author replaced the name of the man who inspired Brahms, Carl Ferdinand Pohl, with a description of the job, like the archivist of the Vienna Musikverein or something like that. And the computer was unable to answer. But the expert human quiz game players would still easily answer the edited questions correctly. And this, if you want to look at the news, you can take a look at the University of Maryland study. Cautionary tales are also important. For instance, North Point built a crime predictor AI for New York County that disproportionately marked the African American residents as possible offenders. So, like, again, Tesla's autopilot mode led to the death of a stranger in Florida due to AI failure. Microsoft chatbot Tay on Twitter turned into a Hitler-loving, feminist bashing troll within a day just by soaking in our humanity. And of course, Chinese government is using mass facial recognition drive for using its AI databases. So all of these should actually be taken into account when you're building application. We work to better humanity, not to plunge us into darkness. But that being said, this is again, like, this was developed by an AI team, which tried to get from like latest fashion and other trends all over the internet tried to suggest only what are the fashionable things that you can wear per season. And in fact, it's still available. You can check it, the marketableai. It seems like a simple thing, but like that, as young people always want to wear what is fashionable, and sometimes they don't have fashion sense, but this can actually help them, and it helps the marketing teams of different kinds as well. Then this was again like this is a strange confluence of art and AI. Like this is in the website called deepart.io. If you can go there, here deep learning is used to extract as if a style from a particular painter. For instance, for instance, on the bottom left, you have a Van Gogh painting, and on the bottom right, you have the painting screen, very famous paintings, like multi-million dollars, hundreds of $1 million paintings. What they have done is they have extracted the style of the painting. And the style of the painting is not just adding texture filters, but actually how the entire image would be styled. And they apply it on the image that you see on the top left. And they get some very, very interestingly different kinds of images. You'll see all the houses, roads, everything get changed into as if the style that the corresponding person would have, a painter would have done. And of course, there are AIs in education like Watson Assistant, which has the true collaboration between human and AI, and which helps in automation and administrative tasks. Trial and error can be made less intimidating, and future of differentiated and individual learning lies in some of these. Go to the next one. So this being the introduction to the AI, I hope if you have any questions or other things, you can ask me so far. Now we'll go to the next part of the presentation. So now that we have spoken so much about AI, and we have shown that how the biological imagination of a neuron has led to successes in AI in multiple different formats. And again, I do not have the time to go into it. Even why do you think deep neural networks have layers? Like those of you who who know, or those of you who do not know, please try to think of it throughout the lecture. Like why do we benefit from having these multiple layers in deep learning? And I'm going to try to answer it from biological side. The reasons are extremely biological. Now, uh, in this fashion, now when you come to brain computer interface, we work with brain computer interfaces because again our brain is constantly working, and brain is giving out certain biopotentials, like the ECG that you do for the heart. You can put actually electrodes on your scalp, and it will record voltage fluctuations that are surprisingly regular. We can actually see how we are thinking from just decoding those biosignals. I'm going to go a bit further. Now we know that in the brain activity comes from firing of neurons, but of course I can't I'm not legally allowed to open another human being's brain and put electrodes in it and get the signals from there. What we can do is indirect recording. Those indirect recordings we do it with the encephalogram. Now in this encephalogram, was always used in clinical purposes. In whichever city you are, there are so many neurological diagnostic centers where you will see that at least 8 channel, 26 channel EEGs are already present, and clinicians use it mainly for looking at epilepsy patients, and try to see that whether the patient is at risk of having a seizure or not. But our purpose is slightly different. We are looking at normal brain activity from neurotypical population. So because there is so much data that is that is apparent if you know where to look for it. It's apparent in the electroencephalogram. Like, first of all, there are few frequency bands that we can see that are very cognitively important. In fact, like this alpha oscillations, 8 to 12 hertz oscillations are seen, especially when you are having a good sleep or you are feeling drowsy. Whereas some of the beta band is seen when you are voluntarily making some action, you are thinking of moving something. Some of these can be constantly recognized almost like clockwork, because by we see the brain signal, we know that what the person was doing or thinking. And why are we able to do that? This picture will give you some idea. So if you look at the just behind our brain, like if you can see at the backside of our brain is where the visual areas are. So our visual areas are absolutely to the occipital lobe is towards the back of the brain. So when you see anything from your eyes, the signal goes directly towards the back of your brain. And from there, the signal starts traveling to the higher order brain areas. Now, if you see here, it's a time ordered graph. So if you see for the within the same time, say you have electrodes, all of these green, light green, cyan, red, and blue electrodes, if you have put, you can almost see as if the signal is traveling through those black lines we have shown, black arrows are pointing out. You can see how, especially when you see something, the signal starts traveling through higher order of the brain. So we know that your brain has started processing from one region to another. So because first of all, at the occipital lobe, there are only those neurons which can only see, say, simple things like orientation. Maybe they can see edges, some junction. They are simple cells, contrast. But if you go slowly higher, by the time you reach the areas marked by red or blue lines, you actually see an entire object. And this is a very reliable way. It happens every time when a human being is shown something. So again, to make actually a technology from any of these biosignals, we need a reliable source of the signal. The reliable source in case of brain-computer interfaces are that our reliability of our own neural processing. So understanding the underlying neural processing can only help in how to improve our this technology. So AI ML techniques and those algorithms are one part, and understanding how the brain actually works is another part in improving the brain-computer interfaces. Now, in case of brain-computer interfaces, we get the data, like some of the predecessors in this FDP have said that we need data. So the data comes from these, again, electrodes placed on different parts of our scalp. It looks scary, but normally we might not, for future BCI applications, we might not need so many. For instance, there are already some BCI headsets available, which basically have just one or two, maximum three electrodes around the middle of the head, and they can function just fine for some of the purposes. So, but yeah, but you can put electrodes in all of those places. Now, when you generate those signals, when you get those signals, how do we measure that whether you're seeing something differently or not? So we can do simple trial. For instance, we can show you a series of X's and series of O's. But maybe the X is more frequent than the O's. And we can time it. We can take your brain signal from, let's say, the center of the head, that is CZ, absolutely central line, center, top of the head electrode. And we take, let's say, window of 1 second after the X was shown, or 1 second after the O was shown. We have so many different kinds of waveforms that are formed. But once we average them, we get rid of all the other noise and we are able to see the shape of the actual waveform, underlying waveform that's available for us. And this is, you see, because the O was less frequent, so whenever O came, you had a surprise factor. And if you have a surprise factor, this P3 peak that occurs somewhere after 300 milliseconds of the stimulus, that is much, much larger than the excess that we're averaging. And that's where the source of most of the BCI come in. Because if we now compare, like, okay, frequent stimulus versus infrequent stimulus can give me a reliable P3 signal that will allow me to make a brain computer interface algorithm. Because I will have a controller device where, again, which will operate based on the reliably appearing P3 signal. If we can detect it, classify it in a single trial, we'll have a very fast BCI. Now, like, this is actually what happens, after we see. Now here, compared to before, like, I have the positives plotted downwards. Please do not feel nothing of it. It's a convention. Again, when you ask the neuroscientists, they will not also be able to give you answers. Like, some of the older neuroscientists 100 years back started plotting the neural data when they used to put actually electrodes to mice or squids. They used to plot the data like this. So we try to show both to appease all parts of the neuroscience community, but ultimately it doesn't really matter. So here the P3 peak looks like it has gone down, but if you see, it's for the positive value. But anyway, now again, you see some of those reliable signals appearing when a person distinguishes between faces versus scars. There is a negative signal that comes around 170 milliseconds that comes very reliably if you see faces, as opposed to seeing any other object. These are the things that allow us to see what kind of paradigm are you going to design, what kind of controller screen you're going to design for the BCI, and some of which I'm not going into because Dr. Ravichandran is probably today or tomorrow afternoon, he's going to explain in more detail about how the BCI's control interface and experimental interfaces are done. But see here, there are reliable signals within your brain we can classify just by taking the voltage from the scalp. And that is amazing. And we can, if you can classify it reliably, we have a BCI system. Now, this part I'm going to skip for a bit, but why we can do that? Why does our brain activity do this? Those of you, or most of you, are from engineering background, you know how electricity and magnetism operate. Now, our neurons act like a oscillating dipole because of continuous polarization and hyperpolarization, like, charging and discharging behavior that the neurons show. And especially for the EEG, we are picking out the neurons that are almost completely vertical as from our scalp. They are called pyramidal cells. They basically maintain connections between different layers of the brain, and because they are vertical, their signals basically can add up, unlike all the other interneurons which are basically like spread in every which way. So their dipoles are not aligned. So in case of pyramidal cells, we have a aligned dipole which oscillates because of neural activity. If there is a neural activity is happening in a particular region, then that neuron will fire. That will lead to like an oscillation of the dipole. And those voltage fluctuations can be picked up by the scalp. And that's what we are doing. And that is why it's very important to understand the underlying brain activity for getting into the BCI. But the problem is that if you see here, now you can have the sources of those different brain activity in multiple different parts of the brain. So you see here the component 1, component 2, component 3, these three different dipoles come out from different parts of the brain, but they will all have some combinations available in all the electrodes E1, E2, and E3. So we need better way to decompose these signals into their components and other things when we are actually studying the brain. And some of it is might be required even in brain-computer interfaces. So just because we are getting a signal in a certain place, that does not mean that's the best place for getting that component. So part of the BCI work is also to find triangulate on which electrodes are most beneficial for the BCI study. And this is where some of the ideas from cognitive science can be a very interesting guiding tool. Now, this is also another example, but again, P300 one that I had shown before, that can be used. But I'm going to skip for brevity's purposes. But yeah, now what happens when we want to control devices using these specific EEG signals from our brain? And that's where the brain computer interfaces come in, because our EEGs can be EEG signals from different parts of our different electrodes can be separated into specific features, which can be used in a real-time classifier built by AI ML technology, and which can be used in turn to control things like a robotic arm, wheelchairs, or cursor on the screen, whatever you wish. Now, the process goes something like this, like you have a stimulation to the brain and your EEG signal is being measured. It goes through a multiple different kinds of process, like pre-processing, feature extraction, classification, and then command execution. And of course, feedback information is passed on to the BCI system again. And this is the simplest flowchart that one can have for processing pipeline. Most of the cases, in case of developing these BCIs, we have an offline trainer and an online trainer. In case of offline trainer, we must just basically try to apply our algorithms, classification algorithms to already recorded data. And in the real time or online applications, we are basically trying to classify it on the fly while the person is giving out EEG signals. And so these BCI's different parts of it are different methods of BCI depend upon these steps: signal acquisition, signal processing, and effector devices. The signal acquisition, it doesn't have to be just EEG. It can be ECOG, it can be local field potentials. We are also later trying to incorporate some of the GSR, greater skin resistance signals to some of these BCIs. But again, then we have signal processing. We have that can be done through different kind autoregressive methods, wavelets, Fourier transforms, Laplacian filters, common spatial filters, and others. And some of these methods will be spoken in detail by others. And there are other effective devices, can be robotic arms, wheelchairs, cursors, spellers, etc. Now, there are different kinds of paradigms for BCI, some of which again Dr. Ravichandar will be elaborating in detail. This is basically event-related synchronization, desynchronization that happens when you voluntarily think about moving a limb, not actually moving. If you think about moving your right hand or left hand or right foot or right leg, that can be obtained from these EEG signals and can be used for a very effective brain-computer interface technology. So mind you, because this is not like motion sensing, this is where you are basically thinking about moving your arm without actually moving it. And there are these stellar matrices for P300 where you have a line of letters that get light up at every second. Like this line will move upwards, downwards, or it will go from left to right. And you have to have a word in mind. Let's say you have the word water in mind. So the possibility of W being lit up is 1 in 36 every time. And sorry, 1/6, because every time 6 letters will be illuminated, there are total 36 letters that the row of W can be illuminated, the possibility is 1/6. So it's a rare event. So whenever W gets illuminated, your brain will give basically a BCI signal for P300, and that's how the BCI will know. So this is how speller matrix operates by utilizing again the surprise element of the P300 that we have spoken before. Now, this is again like this was done in my older lab in BVRIT in Narsapur, where we are trying to develop a like own BCI application. I'm going to show a like some partial success about that in just a bit. And of course, this kind of wheelchair thing was also done for this lady, currently deceased. She was an ALS patient. She was a patient suffering from amyotrophic lateral sclerosis, and so she could not move any of her limbs and arms. So we wanted like her to be able to move her wheelchair or call for help whenever required through this EEG-BCI technology. Again, we reached limited success with that. So what we are going to, the thought I'm going to leave you for this part of the lecture is that you have to think about your own paradigm of the BCI. That's where it all starts. You need to imagine what is the application suitable for BCI. Robotics, assistive technology, VR, what kind of cognitive function you're going to choose. Attention, memory, motor imagery. And you need to justify your choices with a few sentences. This is for your internal that kind of task that you can do. And now I'm going to show you. Let me just. Just 1 second. I have to show. Huh. How much? Uh, can't seem to share the video, but I'm going to share in the FDP WhatsApp group so that you can take a look at. Currently, it doesn't seem to be. I don't seem to be able to do that. But with a few other thoughts, I'm going to leave you with. These are some of the publications from our group, especially because of the collaboration between Dr. Ravichandar and I. We have a few review articles you want to look at where we talk about EEG-BCI classification techniques, advances in experimental paradigms, signal processing algorithms, and like classification technique advancements, and also various signals used for device navigation in BCI production. We have a bunch of those, and we also have like a partial success work, which is going to be published in Nano Life very soon. It has been accepted. We had actually managed to build at least an algorithm for theory-driven BCI with a reconstructed dynamics of EEG time series. We have filed a patent for that as well, where we used our cognitive intuition to try to reduce the lag in BCI learning. And some of you who want to know more of that, you can ask Dr. Ravichandar or me, outside the session. I will stop it right here. If there are any questions, please let me know. Any questions?
Good morning, sir.
Yeah.
Sir, can I ask you one question? That sir, you show some images like that, some small graph, like some red, green color. Sir, what you are trying to show to us? Like, can you explain something? What?
Just I'll open that. Just give me a second. Red, green. Is it where I was talking about the EEG signal in the brain? Just, just a second. This one, is this the one you're asking me about? Hello, Shujit?
No, sir, not this one, sir. Other one, sir. No, sir, no, sir.
Uh,
Other images, sir. Not, no, no, sir.
this one?
No, sir.
No. Is it from this
No,
this
sir.
PPT or the previous one?
Yes, 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 sir. Yes, yes,
Previous,
sir. Yes, yes, sir.
previous one. Okay, okay. Just
Yes, sir. This image only. This image only.
oh, this image only. Okay, just give me a second.
Yes, sir. Yes, sir. Yes.
Ah, okay. Just huh. So this one I was talking about. So this again, I said that Dr. Ravichandar will explain in more detail in other lecture. So I did not want to talk about it too much. But what happens is that whenever you think of moving a limb, either your hand or leg, when you start thinking about it, what happens is that your alpha power decreases. Alpha power of the frequency band, the EEG signal power, like those of you who have done digital signal processing, you will know that we are talking about the power of the signal. So the power of the signal within that particular frequency band decreases. Okay, so whenever you think about moving a limb, so like and it so that's called event related desynchrony. So normally when you're holding an action, when you're not thinking about doing anything, so you'll have alpha power increasing. So I'm not thinking about anything, so there will be a lot of alpha waves, like with 8 to 12 frequency, 12 hertz frequency signals in especially in the electrodes that are shown over there. They're right on the top of your head. There is the central one and one left and one right. So especially looking at those electrodes, these are the kinds of things you can expect. So as soon as you start thinking about the movement, you will see that the alpha power is very high. This red one, you'll see initially you see a lot of alpha power, which suddenly dips because you have thought about a movement. Okay, and this drop is actually very fast, and BCI classification algorithms can pick it up just like that. So this is part of the motor imagery. Imagery because you're imagining it inside your brain. And this is from the
Sir,
brain
how I can
computer.
get,
Huh? Yeah. How?
sir, how I can get idea that if I'm doing any wrong imagination, if my hand is moving somewhat, but I'm
So
thinking something different.
so that's why we need to do a lot of offline testing. So let's say that if you're thinking of something else, then it will not reliably pick up the signal. Like what the setup for this application is that I show you an image of front left hand. Okay. If you see the image of a left hand, then you have to think about moving. So I take the signals from that time onwards. Okay. And if you don't, then then you will have event-related synchrony. Your alpha power will not decrease. So it's timed with you, which is why I said that it will be explained in more detail in a further lecture. My lecture was not exactly about that, but we need a stimulus. You need a stimulation because you even see the speller paradigm has a stimulation. These letters that are highlighted, that's the stimulus that you are getting, and thus your brain reacts to it. In motor imagery, what you will have is basically here you see a dot. Instead of that dot, you will have a picture of a left hand or right hand, left leg or right leg. Okay.
Sir, you are like normally you are using electrode, yeah, like we are using after before something liquid. When I see some person they are
What
doing
liquid?
similar type of research, they are using before putting electrode, they are using some
Yeah,
liquid
that's the electrode gel. For
for
ECG also,
wearing this gadget. So
right,
to
right.
you,
For ECG also, you need a gel. So dry electrodes can't get signals. For ECG also, you have an ECG
sir,
gel
you are also using gel
available
also.
in the market. Right. Here also you can use gel, but gels are different kinds. Like some you can use something very liquidy, but like you need to use small amount. But if you use something like ECG gel, you have to put a bit more. So that's for the impedance of the electrodes to go down a certain level. So for actually proper less noisy EEG signal, you need about impedance of like 5 kilo ohms or lower. Otherwise, you will not get good signal. It will be full of noise.
Thank you, sir.
So if you see, like this is the part I have skipped, but there is one part that I was trying to talk about. That see, this is the range of signals and noises. You'll see that EEG signal is basically somewhere around 10 to the power minus 5 to 10 to the power minus 4 volts. So there can be a lot of amplifier noise and other things that can come in that can disrupt it. So EEG signal that way is like we need to be careful when you are dealing with it. Some of the other devices that are DCI devices that are used, they have their own way of working these problems. So, but that probably one of our other colleagues will talk about. Anything else?
Sir, in your project, how many electrode you have used, sir?
So see,
Like,
I have been using EEG for over 10 years now. So
yes,
I
sir.
have used up to 128 electrodes.
Oh,
So I have used I my training of EEG was in Institute of Mind Brain Sciences in Italy, University of Trento. There we had used 128 electrodes. Then University of Hyderabad Central University. There we had a 64 electrode neuroscan machines. But as you go higher in the electrode count, the price of the equipment increases, of course, exponentially. Currently, we have a 64 EG machine.
thank you, sir. Thank you, sir.
Anybody has any other questions?
Yes. Now we have completed this session on Introduction to Cognition A and BCA, Dr. Rakesh and Gupta, SR University Warangal. Thank you, sir. Thank you for enlightening us with your valuable and informative speech. Thank you very much, sir. So you enlightened us on cognition, cognitive technologies, artificial intelligence, and brain-computer interfacing. From SR University EC department, from bottom of my heart, I'm thanking you for spending your valuable time for this FDP to enlighten the participants with your speech. Thank you very much, sir. Thank you. Now we have a session at 11:50. Okay, na? By Dr. Rahul Chaurasiya, MANIT Bhopal, Madhya Pradesh. Okay? What is of video.
Video. Audio.
Rahul Chaurasiya. Just check. Attendees, go to attendees. Attendees. Good morning, all. Good morning, all. Welcome back to the second session of FDP on applications of artificial intelligence in brain-computer interface, organizing by Department of Electronics and Communication Engineering, SR University. This workshop is FDP is sponsored by DST Cell under social scientific responsibility. Now we have our guest today, second session, that is Rahul Kumar Chaurasiya. Welcome, sir. Welcome to today presentation. Now our sir will give presentation on introduction to emerging applications of BCI, brain computer interfacing. Just Now I will give some short introduction about Rahul Chaurasiya sir. Rahul Kumar Chaurasiya received the BTech degree from MANIT Bhopal in 2009 and ME degree from ISC Bangalore in 2011. He received his PhD degree in 2017 NIT Raipur. He was a senior software engineer with Brockout Communication Systems Bangalore in 2011 to 2012. During 2013 to 19, he was assistant professor at the NIT Raipur, and during 2019 to 20, he was the assistant professor at the MNIT Jaipur. Since 2021, he is with MANIT Bhopal as an assistant professor grade 1. He is a senior member of IEEE. Dr. Chaurasia's research area include machine learning, pattern recognition, brain-computer interfacing, optimization, and biomedical signal processing. He has authored and published more than 50 research articles in aforementioned areas. He has also published one technical book as an author and has completed one sponsored research project sponsored through DST India. He has 2 patents granted and 1 under consideration. He has successfully supervised 1 PhD candidate and is currently supervising 3 more research scholars. Once again, welcome you, sir. Thank you for accepting our invitation. And
thank you, sir, for inviting me to this workshop. It is very relevant to the topic in which I do my research.
Thank you, sir. Thank you. No, sir.
Should I share my screen now?
Yes, sir. Yes, sir. Now you start the sessions.
Okay. Is it visible?
Yes, sir.
Okay. So good morning, everyone. This is a FDP on applications of AI in brain-computer interface organized by SR University Department of Electronics and Communication. So the topic for my talk for today is introduction and emerging applications of brain-computer interfacing. So basically the idea is if you are a faculty or MTech student or PhD student and want to do research in the area of brain-computer interfacing, so this PPT in 1 hour or 1 hour 15-minute session will help you to find the area where you can apply the research or where you can apply your knowledge and publish papers or do some useful work. I have got around 10 research articles and around 20 conference papers published in this BCI area, brain-computer interfacing. So the topics that I will be covering here is first is electroencephalography. Basically, most of the brain-computer interfacing applications are started with acquisition of EEG signals. So I will be giving the introduction of EEG signals. What are the acquisition methods, or if you do not want to acquire, if you want some standard data set available on internet, that also I will let you know. And what are the applications of EEG? Once you know applications of EEG, we know that brain-computer interfacing is also an application of EEG. So I will go with the introduction of brain-computer interfacing. Then what are the applications of BCI? What are the publicly available data sets? And there is one nice free software called BCI 2000. And so I will be giving a small demo of how to use that software for acquiring your own data set, your own EEG data set using this particular system. Okay, so if at any point, if somebody is having any doubt or if somebody is doing any research and wants to ask something or want to collaborate with me or want to work with me, so at any point you can stop me and you can ask if you want. I think some people are at least listening to me, because I have experience of online lectures. Most of the students, they just mute the mic and sleep. So I think at least few people are listening to me. Okay, so what is electroencephalogram? So this is a workshop on BCI. So I think most of you already know what is EEG. So these are the real images captured in my lab for acquiring the EEG data set. EEG denote the electrical neural activities of brain. So it stands for three. It starts with three words. You might have heard the word ECG, very common, electrocardiography. It is basically the capturing of heartbeats. Then there is something called electromyography, your muscle signals, electrooculography. So it is your eye movement. Similarly, electro is basically electrical activity. Encephalo means emitting the signals from the head or from the scalp, and graphy or gram is drawing or writing or studying. It can be electroencephalography or electroencephalograms. Electro is the electrical activity. Encephalo means it is from the scalp. So for example, similar to this, if I have something called ECG, just a minute. So ECG stands for electrocardiography. So it is for heart. So we are basically bothered about the brain signals. So you might be seeing a lot of movies, and in movies we see that ECG. Is this screen visible where I'm writing? In ECG, we have seen there are clear heartbeats. So it's a very clear signal, and it's very easy to have classification of the signal. Okay, and there are very less number of errors because it's a clear. Even our hand can recognize the heartbeat if you touch the heart of a person. But EEG, basically your brain activity, it is not very clear indication. It is whatever is going on inside your brain. So each of the neuron produces a voltage in the range of nanovolt. It is like if you have an iron, they say there are poles like this, north and south pole, but as soon as you try to put a magnet, then they all get aligned, and as a resultant a magnetic field kind of thing is there. So your neurons are continuously producing lots of voltage. There are millions of neurons in our brain, but if you think in a particular direction, all the neurons produce a particular, you can say, particular effect, and based on that, from your scalp you can measure some voltage which is still not very high. Even it is nanovolt in one neuron. Even if you have millions of neurons, the total voltage that you will capture will be between millivolt to microvolt range. It is like 10 to the power minus 4 volt kind of thing. So very small voltage. So you can capture it by applying some electrode and then wire and some device called EEG acquisition device, and then finally you can send it to your PC. So it is not very simple to acquire EEG signals, but still a lot of methods are available and people are doing it. So in this figure, you can see a person is wearing a cap, and from that cap, the electrodes are connected and the signals are acquired through this belt, through this device. These are basically the amplifiers which try to amplify that very small voltage and then send through USB to your PC. So the EEG acquisition methods are basically of two types. Invasive means you are acquiring from inside your scalp directly to the brain. So for that particular acquisition, you need to put holes in your scalp. Okay, that is very difficult and not popular method in human being. But when I was a student in IISc Bangalore, there was a lab called Primates Research Lab. There they were having monkeys and mouse. So they were having some operation over those animals, and they were having electrodes inserted inside their brain. So the very high quality signals were being produced. Those are called invasive methods. So those methods are not popular in human being. So the method that we are using are non-invasive method. It is easy and convenient, but it produces a low quality signal because your head is there. Maybe you will be having hair. You will be applying oil on the hair. So all those things reduces the connectivity and increases the resistance of the connection. Already it is a very low quality signal, and if there is a lot of resistance, the total quality of the signal will be very poor. So there are methods like gel-based and dry electrode methods are available. In gel-based, they put salty gel, which provides a proper connection to your scalp from the electrode. And nowadays, this figure is there. This is an emotive device from a company. it's 14 channel EEG acquisition device. You need to wear it like a headphone only and have a proper connection. You need not to apply gel, so your hair will not get destroyed. Otherwise, in gel-based technology, after acquiring the signal, you have to definitely go and wash your head. And wireless hair gears are also available. So this is also wireless. So there is no wired structure like this. You just need to wear a headphone, and through the Bluetooth, the signals are being sent to your PC. So this device I also have in my lab now. It cost around 2 lakh rupees. If somebody wants to purchase it, or you can acquire the data set, or you can visit some of the nearby institutes to acquire signal if you are working in the EEG field. Okay, so these are some of the images where I have used these things with different students or different PhD scholars. You can see for ladies to use this is very difficult because they are having long hair, and after this you have to definitely wash the gel. So you should have proper washing place inside your laboratory. It is not to be used at your home. This device is not very cheap. So after this you should have a proper washroom where you can wash your head and all. So the acquisition becomes itself a very difficult task in EEG acquisition. But if you have a proper device like this, so it becomes very easy. But obviously this will have a poorer quality signal, and this one will have a very high quality signal. That is the main difference. So where to put on your scale, where to put the electrodes? So there are 10-10 recording system. So what is this 10-10? Basically, from your nose, this in this diagram you can see, it starts from this place and it's go till the back of your head, or in this figure this is your nose, these are your ears. So what actually they do on that scalp area, on your head area, this is suppose your head area. So from this point to this point, they divide and they divide this into 10 parts. So each part is of 10%. So 10, 20. Just a minute, there is some problem. So 20, 30, 40, let me put this here. 50. So this is 10%, 20%, 60, like this. So this is the percentage, 10, 10. Then there is 20, 20, 10, 20. So this is 10, and this side maybe you can put 10% or 20%. If you put 20%, 20, 40, 60, 80. So 10, 10, 10, 20, 20, 10. These are different systems available for acquiring the signals. So this 10% and this. So in 10% there will be total 64 electrodes that you will be putting. If you have 20-20, you will be putting 8 electrodes. Some people use only 4 electrodes. And on your scale, they have divided the region. This is called frontal region. F is for frontal region, T is for temporal region, P is for parietal region, occipital region, and central region. And each region in your brain has different kind of response. So maybe this particular output and this particular output are totally different. That means the output which you produce from TP8, which this is your extremely right side of the brain, and T7 is extremely left side of the brain. The brain's functionality is different, so different kind of signals will be acquired. So it is also an important issue where to put the electrodes. Suppose you have only 4 electrodes, so whether you should put in the central or in the frontal region or in the occipital region, that is also a topic of research. So I have published papers only on deciding which area we should put the electrodes. Okay. Any doubt here to anyone? Otherwise, we'll continue. Has anyone ever used this device or ever seen this device? I want to see if somebody is actually listening to me or not. Can you raise your hand if you have ever seen an EEG acquisition device in your lab or in your institute or in some other lab? Anyone? Okay. So let me go back. Maybe you have not seen it. So once you have acquired the EEG signals, like we teach to our students that audio signals are in the range 300 hertz to 3 kilohertz. But when you acquire the signal, it also contains noise and other kind of signals. Similarly, it happens with, just a minute, I want to put charger. Okay, similarly with EEG, when you are acquiring, there will be your muscle movement, there will be your eye movements, there will be your movement of body. So it will acquire the signal which is not also EEG, it can be noise. So actually the EEG signals are in the range 0 to 50 hertz. And outside signal are maybe because of your eye movement or eye blink or maybe your muscle movements. So that you need to filter out. So there are several types of filters available, Butterworth filter and all filters in MATLAB and all. So those filters we can apply to detect EEG signals. Once you have got the EEG signal, which is in the range, say 0 to 50 hertz, you can divide it into sub-bands. So there are methods like DWT, discrete wavelet transform. Suppose you have a signal of, say, let me write it here. Suppose you have a signal of 0 to 50 hertz. Then what you can do, you can divide that into two-part, detail component and approximation component. So the approximation is basically the low frequency part, 0 to 25 hertz, and detail component is high frequency part. So this is 25 to 50 hertz. So suppose you are getting this signal. So this has two component. First is like this, basically something like this. Inside it, you can say this is the low frequency part. So this is your approximation part A1. And with that A1, you have those high frequency terms. If you add A1 plus D1, you will get back this original signal. A1 plus D1 is your original signal. So this way you can have one order DWT, one order discrete wavelet transform that can divide the signal into two parts. This you can again divide. So this will give you D2 and A2. So 0 to 250 to 25 hertz. So this will be around 12.5 hertz to 25 hertz. And this will be around 0 to 12.5 hertz. So this further has been, this black line has been divided into two parts, the approximation and detailed. So like this, it can be divided and different. So this you can see 0 to F, F by 2 to F is a detail component. This is approximation. Again, you are on second level DWT, third level DWT, like this you can do. So based on that, you can find different sub-frequency components of EEG, which is in the 0 to 50 hertz range. The different sub-frequency component have been given standard names. So 0.5 to 4 hertz is called delta signal, and it is useful for deep sleep. This is a very low frequency signal. So if you are sleeping properly and you are in deep sleep, your brain will generate very low frequency or 0 to 5 hertz frequency signal called delta signals. So if I see other way around, if a doctor wants to say whether you are having a proper sleep or not, so what he will do, he will acquire your EEG signals while you are sleeping and will try to see how much delta component it has. If it is having a proper delta component, that means you are having a deep sleep. If you are not at all having a delta component in the EEG signals required from your brain, that means you are not going in a deep sleep. So every person should have a deep sleep of at least 2 to 3 hours per day. Otherwise, you may get ill or your health will not be good. So this is one of the applications of electroencephalograms or EEG to find whether the person is having a proper sleep or not. Okay, then a little bit higher frequency component, say 4 to 8 hertz, is called the theta waves, which is for light sleep and meditation. So if you are having very anxiety and very much unstable brain, people say go and do the meditation. So in going to the meditation, that means they want to say your brain should be stable. Those neurons inside your brain should be stable. They should not think much. They should concentrate on one thing. So whether you are in light sleep or you are meditating, you are thinking about something, your brain should produce the theta component more. Okay, so which component is more? That shows whatever your brain is functioning at. 8 to 13 hertz is the alpha component, is the eye closed and physical relaxation state. Then 13 to 30 hertz is beta, that is for alertness, focused problem solving skills. So most of the brain computer application data acquires alpha and beta signals. Your eye should be closed, you should be physically relaxed, and at the same time you should be alert to focus on the problem that you are solving. Okay, then only you can apply brain computer interface. What is brain computer interface? Basically, from your brain you are giving direct signal to the computers. So for giving the direct signals to the computer, you should be physically relaxed. At the same time, you should be focused on the problem or alert. And very high frequency EEG signals are for hyper alertness and for integration. So this is very hyper alertness, that is not very, very useful. So sometimes people only use this 10 to 30 hertz signal for brain computer interfacing parts. They use the low frequency component signal for sleep detection or meditation purpose and all, and this high alertness signal basically shows that your brain is not stable, you need to do meditation, you need to see doctor, or you are thinking too much. Those are the problems if the gamma component is more in your EEG signals acquired from your brain. So from brain, your mental status can be told by doctor very easily. So this is the method of dividing the signals into subcomponents. DWT is the most commonly used method. There are different kinds of wavelets. Haar wavelet is there, and other kinds of wavelets are there. So you can use any one of them. So this is the example. This is the sample data. Then A5 is the lowest component frequency signal, 0 to 2 hertz, which is I am saying is the deep sleep signal, which is very slow signal. Then you are going to higher range, 2 to 5 hertz. Then 5 to 10 hertz, 10 to 20 hertz, 20 to 40 hertz, and 40 to 60 hertz. This is even higher than the EEG signal component. So this shows how using 5-level DWT you can divide a signal which is in 0 to 173 hertz range into different parts. Alpha, beta, gamma, delta kind of signals you can divide. Okay, so we have come to know that EEG are basically the brain responses that are very low frequency or low amplitude signals, but generated by brain. They are generated in different activities, whether you are sleeping, whether you are alert, whether you are hyperactive or something like that. So the applications of these signals are in brain computer interfacing. They are also in neurology. So they can be used to detect epilepsy disease, memory problem like Alzheimer's, seizure detection, sleep signal analysis, anxiety detection, coma detection, level of consciousness of a person, whether you are being properly conscious or not, study of mental disorders like psychiatric disorders. And this is a new topic called neuromarketing. This is still a research topic by commercial companies. For example, Amazon. One of the newest branch of the advertisement industry aims to understand the consumer's need, behavior, and emotions and forecast their decision-making process. So maybe like Amazon, suppose you are going to Amazon website, they are having millions of products to sell, but on your screen, they are showing only few of the products. So they record your response, whether you are happy to see those products or not, whether you are having an anxiety or not, or you are just being dull by seeing those products. So they are doing marketing based on your neural response. So that is called neuromarketing. They try to understand your behavior and emotions based on the product that they are showing to you. So it's a product recommendation system based on your neurological response. So this is also a new research area by the advertisement companies. This neurology is basically by the doctors, and brain computer interfacing is basically to generate a new augmentative medium of communication for physically disabled person mainly. So my research is basically in the first part, brain computer interface. So what basically is a brain computer interface? A brain computer interface is a direct communication pathway between a human brain and external device. So suppose external device is your fan or your TV or your wheelchair, and you want to move it without you using your hands or without even speaking. You just want to think in your brain and it should react accordingly. That is what is brain-computer interface. It's a direct connection from brain using those EEG signals to that particular device without your other skills, talking, gesture, writing, etc. Okay, so it is mostly useful for people in coma or people which are physically disabled or which cannot do motor activity, which cannot move their hands, which cannot talk, but still want to communicate with people. So you have to start with acquiring the EEG signals from the person. You have to do pre-processing like filtering the signals, dividing into subbands. Then you have to acquire the features. Features can be like energy of the signal. Then maybe you can have a mean of the signal, autocorrelation functions. So whatever statistical feature you can acquire that. Then you will have to apply classifiers. Classifiers are like maybe SVM classifier, KNN classifier, ANN classifier, or deep learning method, recurrent neural network. There are lot of CNN classifier you can apply, and you can handle a brain-computer interfacing application out of that. Okay. So the example application, this is the research done by one of the PhD scholars whom I have supervised. So this is the real work which we have done, and these are the real pictures. So what we have done, we were having a laptop. It was running the GUI app, or it was running the software called BCI 2000 software. From that software, we were having an extended screen. So the screen, which is normal PC screen, that was being displayed. On that screen, we were displaying different devices to the person to which he wants to operate: TV, mobile phone, door, heater, fan, light, like these. And a person is focusing on them. So based on his response, we can detect whether he wants to operate a TV, or whether he wants to operate a mobile, or whether he wants to operate a door. So those EEG responses are coming to our amplifier. Amplifier amplifies those signals, and then from the optical fiber cable, it sends those to USB adapter. USB adapter converts those signal to normal data form, and through the USB signal, they go back to your PC. So the flagging is important. At what time, which picture you have shown, and what is the response from your brain, that is very important, because it is in the millisecond duration that delay should happen. Then only it will be properly able to tell whether it is detecting the signal or not. Okay, once you have detected, suppose you have detected the TV, then through Arduino board, we will send the command to TV. So what are the different commands? We can turn on the TV, turn off the TV, or we can change the channel, we can put volume up or volume down. For mobile, there will be different options and all. So there are different devices which you can connect. So this is basically the smart world created for the person which are physically disabled and wants to operate devices using this. So this kind of research we have done. So what are the applications of P300 Speller, brain-computer interfacing? First application is called Speller, or called P300 ERP-based Speller. So I will tell you what is P300. Basically, when I was showing you the TV and mobile and all images, what happens there? Suppose you have shown the mobile to person at this time, t is equal to 0. So your EEG signal for that mobile will have a peak. Like in an ECG, I am saying this kind of signals are there. So these are called peaks, and it's a positive peak. So it's a positive peak. It after 300 millisecond of the stimulation. So this is called stimulation. I am stimulating the subject, and this is your brain response. Brain response as positive. P stands for positive peak at 300 milliseconds. So this is called P300 response. Then ERP. ERP stands for event related potential. So it's a potential, basically it's a voltage signal. This is the time scale. Event related. You have given some event at some time as a stimulation, and after 300 millisecond, a positive peak is observed. So it is called P300 stimulation. So this is the most commonly used BCI application, P300 ERP based spellers. I will show you a demo of this in this particular lecture. Then you can use the brain computer interface for wheelchair control. You can use it for keyboard control or 2D cursor control. You can move your mouse or you can type on your PC by just your brains. It can use for mobile screen control, robot motion control, drone control, control dashboards of a vehicle, controlling artificial body parts like arms. So this is also very important, artificial body parts. Some people may not be having hands or feet, but they want to move it. So from your brain, you can send the signal and your artificial hand will be moving. So that is controlling the artificial body part using BCI. This is very interesting application. And home appliance control system is also very good application. So I have worked on two areas, spellers. This is called P300 ERP based speller. My PhD was on this topic. And I have supervised one PhD on home appliance control system. What is a P300 speller? A P300 event related potential, because it is generated in the response of an event, is BCI system that enables a subject to communicate to computer machine without performing muscular activity. So you can type, you can write in any language. It can be Hindi, it can be English, Chinese, Tamil, Telugu, Kannada, in any language by the characters of the spelling. It imitates a P3 computer keyboard. Basically, in computer keyboard, you are typing by hand, but in brain computer interfacing, you are typing the characters using your brain, not using hands or not by speaking. It's an augmentative, that is something new, a new medium of communication for people suffering from various motor disabilities. They are not able to move or do some muscular movement and are not able to communicate by muscular activity. जो लोग बोल भी नहीं पा रहे हैं, they are not able to speak, they are not able to talk, they are not able to move the hands, but still their brain is functioning. Maybe they are in coma, but brain is working, or maybe they are physically handicapped, but the brain is working. They can use this particular application. So what are different parts if you are doing research in this area? First, you have to visually stimulate a subject. So that is called display paradigm. That means you have to give him the characters which he wants to type. For example, if you want him to type in English, you want to show him all the A, B, C, D, E, F, G, H, I, J, K, all the alphabet, all the numbers. If you want him to type in Telugu, you have to give him all the characters. Or if you want to talk him in Hindi, you have to give all the characters as input or stimulation. Then he will be focusing on some of the characters. So you have to record the brain activities in terms of EEG signals. So you have to have a EEG acquisition device. Once you have recorded those response signals, you have to pre-process the recorded signals. Maybe you want to reduce the sampling rate. Maybe you want to filter out the noise. Then you will do the feature extraction. So you will take useful features. Okay, then you will apply the classifier to find which character he wants to communicate. And this all should happen in a very less amount of time, maybe 1 second for one character. Okay, otherwise, if it is very slow, a person will be typing his name and it will take 2 minutes to type his name only. So per character should be very less, 1 second, one character. So maybe your name is of 5 character, it should take 5 seconds to type. So the most important thing in P300 speller is it should be fast, it should be accurate. Otherwise, if it is not fast, nobody is going to use it. If a person is going to type it, normally we are very fast in typing. But if you are typing your brain, then also it should be very fast. And then sometimes you have to do the post-processing of character detection and all. So this is the general diagram of BCI, brain-computer interfacing, which is P300 speller-based. You have to display the matrix for eliciting P300 ERP. Display the matrix of characters. And a person will be seeing those displays. His brain signal will be recorded. So we will be having the EEG data and we will do the pre-processing. Then you will have to select the channel sometimes. That means which electrode I will be using for classification, which electrode data I will be using. Data transformation and dimension reduction. Maybe you can apply PCA method of machine learning, principal component analysis, or method for dimension reduction. Then you apply classification methods and then you detect the character. Okay. So this is The first P300 speller system that was proposed in 1988. It's a very old topic of research. It was proposed in 1988. First 1988 was the first P300 speller for English. Obviously, the first one was in English. It consists of 36 characters, 24 characters, and some numbers. So 26 plus 10, 26 plus 10, 36. So 26 and then numbers 1 to 9 and this space. So this was called as row column paradigm. So what they do actually in this, they have this display on your laptop, this black screen, and randomly intensify this white. So you can see that MNOPQR, this row is intensified. Sometimes different column will be intensified, and it is randomly and very quick. Okay, so when it is random and very quick, so suppose you are focusing on H. So whenever second row or second column intensifies, your brain is focusing on H. And because of very high light coming on your brain is alert mode, they will generate the P300 ERP. So what is your task? You have to detect that H by processing those signals which you are acquiring. So this way you can, next time you can detect I, next time you can detect V, like this you can do. So this was the first P300 paradigm. So this is called row column paradigm, first one, A. Then some people came up with the idea of single character paradigm. So they were, this display is called paradigm. They were intensifying only one character at a time. So it was very slow. Out of all 36, randomly they are intensifying. Then there is called checkboard paradigm. Either all the rows or columns of white one will be displayed or the black one will be displayed. Then there was region-based paradigm. So first they intensify one region. Once the region has been selected, then they zoom out, and out of that region they intensify the character. So what is the principle of P300 speller? It works on the concept of oddball paradigm. Odd means probability is less. What are the odds? They say. So what is the probability? A subject is stimulated with a series of events, and his task is to determine the true class of events out of two different possible. So called oddball. The rare event will elicit P300 ERP. The series of experimental augment is called oddball paradigm. So suppose you are showing a person lot of cricket balls, and suddenly you show him one football. Suppose out of 10 there are only one football. So what is the probability that you will show him the football is 1 by 10. So that probability is less. So that is the rare event. So the rare event will generate P300 ERP in the signal in the brain of the person. The more frequent one will not generate any response. So in this you can see, suppose you are focusing on H. So out of 6 rows and 6 columns, total 12 rows and columns are there. Only 2 rows, the second row and second column, will generate that H will intensify H. So 2 by 12 is the probability that H will get intensified. Probability is very less. Lesser probability, higher the chances of P300 ERP. So it will generate a P300 ERP. Your task is just to detect when it was generated. Okay. So this is an example. The normal signal, that means other rows and columns are being intensified. This red signal is the response of that particular time. You can see it's a normal EEG signals, and lots of brain other activities are going inside your brain. But when you see this blue signal, that is generated when your brain is focusing on a character, suppose H, and then H is being intensified. So you can see suddenly a very high voltage is being generated, and that particular high voltage is called P300 ERP because it's generated after 300 milliseconds of the stimulation. So what is there in the paradigm? When you are training the model, the classifier model, so you have to get the training data. So for training data purpose, you will decide that a person should focus on this. Suppose S, E, and D. You will ask him to first focus on S, then maybe focus on E, then focus on N, then focus on D. And this is the text which he will be focusing on, and this is the result of the classifier system. and this is the speller display. So this is the most commonly used classifier. But what happens? Suppose a person is focusing on H. Okay. But maybe he has missed that H one times, or maybe at the same time he has blinked the eye, or maybe he has moved his muscles. So that P300 ERP which you are seeing here might not be as accurate as in this case. So it will be difficult to detect it. So we have multiple trials. Multiple trials means you were repeating again and again the same experiment. All rows and columns you are intensifying very quickly. So several times he will be focusing on H. So the computer will detect that whenever H is there, then only ERP is coming. So after 2 or 3 trials, that means after 2 or 3 intensification of H, computer will be sure. So that is called multiple trial system. That has more chances of accuracy, but lesser is the speed of typing. Obviously, for typing H, you are detecting the signals multiple times. So the accuracy is more, but the speed is slow. Okay. So what was the work done by me in PhD? And also I got a DST sponsored project for the same. Instead of having this, yes, any doubt? Any doubt to anyone?
Good afternoon, sir.
Yes.
Hello, good afternoon, sir. Sir, can I ask you one question, sir, about the data set you have showed us, like sample data set, where we can download that data set?
Download the data set. Okay, I will give you one link in this PPT only. I will tell you where from where you can download the data set. Okay.
Thank you. Thank you.
So the data set is available on internet for this RC paradigm of 36 characters. Okay.
Sir, just share that link or.
I will share. I will share this entire PPT. It will have the link. It will have full details of where you can download. I'm coming to that page only after this. Okay. So this was the work done by some people for English. So what I have done, I have used Devanagari script. It consists of Hindi characters. So it has 1, 2, 3, 4, 5, 6, 7, 8. So it has 64 characters, 8 by 8 matrix of numbers and characters. Also, I have backspace, question mark, space, and hash. Hash I was using for using ardhakshar or matra. So suppose I want to use E as a matra or E as a character, so I can decide using hash. So this display paradigm was designed by me, and I acquired the characters. I applied the classifier. So I did my PhD on this and published few papers, and also DST sponsored research project was on this. So through that project we purchased that machine, EEG machine. So this was the complete picture. We have the computer screen, and here we were displaying the Devanagari characters. The signals were being recorded, and through this Arduino board part is not there. So actually, what was the drawback of this? More number of characters. Obviously, in audible paradigm, signal will be stronger, so classification will be easy. But in detecting more characters is more difficult. Number of characters are there more, so persons get confused. Some of the characters are similarly looking. Suppose O and OW, and a person is by mistake focusing on different things, then it becomes difficult to acquire the signal. So there are some difficulties which are involved in crowding effect by the characters. More number of characters are there. So in Hindi, there are different problems. Not Hindi. This basically is the Devanagari script, which is used for Hindi, Sanskrit, even Nepali, and Marathi. So a lot of language use this script. So it can be used for them. So then once I completed this work, then I moved towards the hardware side. We developed a home appliance control system where we were having TV or fan or light bulb mobile like this. So suppose you are having a TV, then you can have channel down, channel up, power on, power off option. So this different options. For phone, you have the options of dialing a number. For door lock, you have this option of lock and unlock. For fan, you are having the option of speed. For light, you are having option of on and off, and for heater also the options are there. So we did the data collection for home appliance control system as well. We pre-process the data, applied latest neural network called EEG-net. So EEG-net is basically a neural network which has been designed especially for EEG signals. So that network we have used in Python. Then target P300 ERP we have detected, and once the system has been detected, we have used Arduino board to operate that particular appliance. So that appliance was having the smart like sensors which can detect the signal and acts accordingly. Okay, so this is the link which I was saying, publicly available data set. So this is the first link. Let me go to this. This is called BCI competition 3. So they have different data sets, session 2, session transfer, data set 4A. So data set 2B is basically the data set which you are using. This is called Berlin BCI competition. It was held in 2004 and 2008 and all. So data set 2B is the P300 data set. This data set 2, if you can see, is P300 speller paradigm data set. The description is also there. So they will show you what was the paradigm, the same paradigm they have used, how they have collected the data, which system they have used, okay, which row and column they have used. Everything is there, detailed in this paper, and the data set is downloadable. You can download it and can you put in MATLAB or maybe in Python, and you can work with that. Then there are different data set, motor imaginary data, sleep data, and all. So there are two basic data set which are very standard, and most of the people publish their work on this. BCI competition 3 data set and BCI competition 2 data set. Two happened in 2004 and this happened in 2008. Please mute yourself if you are not talking. I will ask organizer to mute other people because it is creating noise. Okay, so this was about the data set, BCI competition 2 and BCI competition 3. Even on Google, if you write BCI competition, it will send you to the link. So, but when you will try to download the data set, they will ask you to have a login. So you will have to put your email ID and password and will have to sign that I will not use this data for commercial purpose and I will be using for research purpose. You will put OK. Maybe after 1 or 2 days, they will approve your or authenticate your login. Then after that, you will be able to download the files because they do not want people to use that for commercial purpose. That is to use for research purpose. So 1 or 2 days are taken in authentication from their side. Then only you will be able to download the data set. Okay, so this is about the data set. There is also a software from the same website you can go and you can download a software called B300 BCI 2000 Contrib. Suppose you want to acquire signals like I have done for Devanagari script. So from the same software, you have to stimulate the subject and record the signal. Otherwise, how you will know that after 300 milliseconds you have to acquire the signal? So it has to use some software. So this software is freely available, BCI 2000 Contrib software for acquiring the data set. So it can be used for data acquisition. You can decide, run, character, and other things. I will just give you a very simple demo of this. So this is how the software looks, or maybe I go to the page. Let me go to the page from where I can do that. So I have downloaded this, and whenever you want, you can run it. So it has got some of the files there, and one file I have selected and I have run it. So this is it, BCI 2000 launcher. So signal source, I'm having in this case a simple signal generator. Signal generator means some hypothetical signal it can generate. or you can have, there are different devices commercially available, biosemi, emotive device I'm having in with me. NeuroSky devices, they are available in market. NeuroSky is very simple. It costs only 10,000 rupees. I went to SRM University, Chennai. People are using this device. It costs only 10,000 rupees. You can purchase and you can acquire your own signal. IDA client, remote data access client. So there are a lot of devices available. They try to accommodate all of them as signal generator. So I am having here a signal generator. A big class. Then application. Application may be like I am selecting P3 signal processing, P300 signal processing. Application is P300 speller. And you can have application like VCI and all. So I go and launch. Let me allow this thing. Then you have to configure. Configure means you have to decide how many rows or how many columns you want, visualization, system, source, from where you will get the signal, where you will store the signal, which kind of digital filter you want to apply, and connector and application. So sometimes you need to do all these things. So I have already done this. So I have saved this as PRM is parameter, demo parameter. They also give you some demo parameter. Okay, so this you have done. Then you have the set config. So in set config, this is my display paradigm, which I can even shift to new screen. I can extend this to new screen. This is the response that will be visible. So now you can see this screen. This is completely blank. That means no character or row column is being intensified. In the configuration, you can decide for how much second it will be displayed and for which kind of randomness will be there. Okay, and where the response will be saved and what target you want a person to do. And then you start. So you see here. We give 2-3 seconds time for a person to relax and then focus. Now you can see very quickly all the rows and columns are being displayed. Maybe it is too fast and maybe because of slow internet, it will not be properly visible to you. So suppose you are focusing on the character, say cha. So whenever the cha is being intensified, your brain will generate a signal, and that will be acquired by the software itself and will be stored wherever you want. And using that signal, you will be using it offline in MATLAB or something. Then you will be detecting or training the classifier. Online also can be done. Okay, so this I have done for 4 characters and 15 trials. 15 trials means 15 times that particular character should intensify. Okay, so it will go long for maybe 4-5 seconds. One character is done. So whatever was the character and what is it has detected, those things are coming in. Okay, so suspend and quit. So this software also you can use if you are willing to learn it. You can talk to me personally, but I was just wanted to give you a demo of how you can use this software. Okay. So I will go to the summary.
Hello.
Yes.
Hello, sir. Sir, can you share the software link so I can go through that also?
If you Google and you type BCI 2000 contract, so it will give you to this page, or maybe BCI 2000 only you can also use. So it will go to the page. It will take you to the link. As I already told you, you have to log in that. Using it whenever people start to download, your username and password. So this they also have
Thank you, sir. Thank you, sir. Okay, sir. Okay.
to use it, how to do contributions and all that. There is there. Even they have forums to discuss. If you are having some problem and you are not able to use it properly, then they will help you. Even I have done like this only. I have downloaded it. I was not able to use, so I posted my question there. They have answered. Oh, and that way I have learned all this. Okay. And if you want to work mostly on the classification side or maybe on the machine learning side and do not want to acquire the signal, then you can directly download the signals for different applications, maybe for brain-computer interfacing, for sleep detection, for Alzheimer's detection, for epileptic seizure detection. There are several data sets available. Okay, so you have to put your name and email and you can download the data set. And you have to put this or cite this particular paper when you are using it. So a lot of paper have been already published, VCI competition 1, 2, VCI info, VCI 2000 software, everything is there available here. Okay, so I will go to the summary.
Thank you, sir.
In this particular session, I tried to cover electroencephalography, basically EEG signals, which are generated from your brain and are very low amplitude signals. So you need to have proper amplifiers. Afterwards, you have to filter them. So you can have DWT, and after filtering, you can divide them into subbands. This is very important slide. Different subbands are responsible for different kind of brain responsibilities. So if you are working on deep sleep detection, you have to work on delta band, then theta. These are the standard things which are available in every book of EEG. Theta band, alpha, beta, and gamma bands. Alpha and beta are more useful for, say, P300 speller or brain-computer interfacing. Theta and delta are more important for meditation. So one student did one very interesting research. They were finding the percentage of theta in your total EEG. If it is more, they are saying you are having a proper meditation. So suppose they are having 10 students inside a yoga camp. So who is having a proper meditation, they can detect by detecting the theta component. Whichever student is having more theta component, they are having better meditation. So other way around, they can say if you are having proper meditation, your brain will be relaxed. So that is you can say scientific method of proving that meditation can relax your brain, because your theta band will be more and alpha, beta, and gamma will be less. Gamma will be very, very less. Then we have discussed about applications which are in neurology and BCI and neuromarketing. BCI is brain-computer interfacing. I have used it for P300 speller for Devanagari script. Also, home appliance control system, I have used it. So you can design your own paradigm. People can design. Some people have designed this for Japanese and Chinese and maybe in Iran some language. But still in Indian languages like Telugu and Kannada and lot of languages, still it is unexplored. People have not used it with other language. So what are the difficulties they are facing? What are the challenges with those languages? Those all should come here. In Chinese, they say there are 47,000 characters. So it was a very high level of difficulty. In Chinese language, they have 47,000 characters, how they can display it. So they were having different, first level, they were detecting the very basic shape. Then they were going to the larger shape. Then finally, they were going to a set of characters looking like that shape. So changing the display again and again. So that was very difficult for them in Chinese. There is a research paper published on Chinese character detection. In Hindi, that difficulty came because the number of characters are more, so crowding effect increases. The similar looking characters like this O and O or Pa or Fa and maybe Sa and Sha. So this character creates problem. So this in the response, the signals become weak. P300 ERP become weak. So we have mentioned these challenges, and based on that, we have published the papers. And also, as I already told, there are software open source data set available if you want to download the data set. If you want to acquire the data set, then you can use BCI 2000 contract software. Okay. So if you're having any doubt, we can discuss it now. Any doubt to anyone or any question?
Excuse me, sir, I have a doubt.
Yes.
Sir, do we have a data set for Indian languages also in BCA website?
No, that is 2-3 standard data sets are there. They were recorded in 2004 and 8. Still, a lot of people are publishing papers. They are applying different modern machine language. machine learning applications like CNN or deep learning or EEG-net or those kind of things. So they are standard data set, as I have already shown to you. Both of the data set has been acquired with this particular display paradigm, 36 character paradigm, and for sleep and others they do not have for Indian language, even they do not have for these kind of single character paradigm, region-based paradigm. But this region-based paradigm was published by one other researcher, and if you search on internet, their website, they are having the data set for this. So it is not available. The data set is not available for Indian language and BCI. In fact, I think it is not available in any software platform, because I have worked on that, and there are some people working in NIT Rourkela, few people who are working in NIT Kanpur, but none of them has put their data set on internet because they are keeping on working on that. So they do not want to share their data set. So it is good that if you want to work, you can purchase the device Emotive or NeuroSky. NeuroSky is not very costly. I also have it in my lab that you can use and acquire your own data set if you want to work on Indian language data set.
Okay,
Any
sir.
other
Thank you.
question? Any other question? If there is no question, we can end this session then.
Yes, dear participants, any questions? Okay. So we will conclude the session, this one. Thank you, sir. Thank you very much for enlightening us with your research experience. You have a vast experience in the field of brain-computer interfacing, and you have given from basics to research level. You have given information from basics to research level. Thank you very much, sir. You have explained in a simple manner. Everyone can understand that one. Thank you very much, sir. Once again, from the bottom of my heart, I would like to tell thanks for you on behalf of SR University EC Department Organizing Committee. Thank you very much, sir. Now we have a session at 2 o'clock by Dr. Ram Vilas Pachori, IIT Indore, Madhya Pradesh. The topic is automated systems based on signal processing and machine learning for identification of EEG signals. So thank you, sir. Thank you very much. Rahul Chaurasiya, sir. Thank you, sir.
Okay, sir. So as you have mentioned the name of Professor Ram Vilas Pachori, I would like to share with you here about
Yes,
one of our book we have published. Today only I got the mail morning that your book is
Yes, sir.
published. So I will just show you the name. It's a book with the name AI Enabled Smart Healthcare Using Biomedical Signal. I am the main author, and Ram Vilas Pachori sir is co-author in that book. So in that book, we have published a lot of work related to EEG signal and brain-computer interfacing.
Okay.
And if some people want, they can download the papers from that book and can use it. Okay,
Yes,
sir?
sir. Thank
So
you,
we
sir.
end
Thank you
this
very much,
session.
sir. Yes, sir. Thank you very much, sir. Okay.
Leave now? Can I leave now?
Yes, sir.